There are no storms on the moon, no clouds, no lightning. The lunar surface is a realm of eternal silence, where nothing moves except shadows crawling across ancient dust. Or so we thought. Because on December 12th, 2025, something impossible lit up the darkness, a flash so bright it could be seen from Earth, erupting from a place where no light should exist. For 0.8 of a second, a spot on the moon's shadowed face burned hotter than the surface of the sun. This wasn't a technical glitch. It wasn't a reflection or an optical illusion. It was violence, pure, kinetic, cosmic violence. And for the first time in human history, we watched it unfold in real time. What caused that flash could rewrite everything we think we know about the safety of space exploration. And what it means for humanity's return to the moon might be the most important question we're not asking. The moon has been humanity's silent companion for 4.5 billion years, circling our world in cosmic solitude. We've walked on its surface, we've planted flags in its dust, we've even hit golf balls across its airless plains. But for all our exploration, for all our romantic fascination with Earth's only natural satellite, we've missed something critical, something dangerous. The moon is under constant bombardment. Every single day, rocks from space, some no bigger than grains of sand, others the size of cars, slam into the lunar surface at speeds that make bullets look like they're standing still. Without an atmosphere to burn them up, these cosmic projectiles hit with the full fury of their velocity intact, each impact releasing energy that would shame most conventional explosives. For decades, we knew these impacts were happening. Mathematical models predicted them. Ancient craters testified to their violence. But actually seeing one occur? That was like trying to photograph a specific raindrop in a hurricane. The moon's surface spans nearly 15 million square miles. An impact flash lasts mere milliseconds. The odds of pointing a telescope at exactly the right place at exactly the right microsecond seemed impossibly small. Until that December night, when impossible became reality. The Geminid meteor shower was reaching its spectacular peak, that annual celestial fireworks display, when Earth plows through the debris trail left behind by an object called 3200 Phaethon. While stargazers across the planet turned their eyes skyward to watch shooting stars streak across our atmosphere, a robotic telescope in the Canary Islands was watching something else entirely. This wasn't some graduate student's hobby project. This was MIDAS, the Moon Impacts Detection and Analysis System, specifically designed to catch these phantom events. Its digital eye was locked on the moon's unilluminated region, that band of darkness where lunar night reigns, where the contrast between black regolith and impact flash reaches its maximum. Then it happened. Frame 2447 of the night's observations, a burst of light erupting from coordinates that moments before had been absolute darkness. The flash lasted less than a second, but in that fraction of time, the temperature at the impact site exceeded that of the sun's surface. Lunar soil vaporized instantly. Rock that had sat undisturbed for eons became incandescent plasma, expanding at hypersonic speeds. But here's what makes this extraordinary. The observation team saw it happen. Not hours later, while reviewing footage. Not days afterward, during data analysis. They witnessed the impact in real time, their screens illuminating with the flash of cosmic violence occurring 238,155 miles away. For the first time in the history of ground-based lunar observation, humans had caught the moon in the act of being wounded. Now the real detective work began. A flash of light might seem simple, just photons hitting a detector. But buried in that brief burst of illumination was a treasure trove of forensic evidence. Each wavelength told a story. Each millisecond of the flash's duration revealed secrets about the impactor's composition, velocity, and origin. The analysis revealed something remarkable. This wasn't just random space debris. The timing was too perfect, the trajectory too aligned. This object was almost certainly a fragment from 3,200 Phaethon's debris stream, the same cosmic river of rock that creates the Geminid meteor shower. While its cousins burned up in spectacular fashion as they hit Earth's protective atmosphere, this particular fragment had a different destination. The numbers are staggering. Impact velocity, estimated at over 72,000 kilometers per hour, fast enough to circle Earth's equator in less than 35 minutes. The object itself? Probably no larger than a softball, maybe even smaller. But at those speeds, size becomes irrelevant. Kinetic energy transforms mass into a weapon. The impact released energy, equivalent to hundreds of kilograms of TNT, detonating simultaneously. The resulting crater, now somewhere on the moon's surface, waiting to be identified in future high-resolution surveys, probably measures several meters across. Not large by lunar standards, the moon's face is already covered with impact scars, ranging from microscopic to massive. But this one is special. This one we saw being created. And here's where the story takes a darker turn, because that crater isn't just a curiosity for scientists to study. It's a warning. A preview of the threats that await any human settlement we establish on the lunar surface. Think about it. No atmosphere means no protection. What burns up harmlessly as a shooting star on Earth becomes a hypersonic projectile on the moon. Every meteor shower that dazzles us from our backyards represents a barrage of potential impactors for lunar habitats. And unlike asteroids, those massive, trackable threats we've spent billions learning to detect, these smaller objects are essentially invisible until the moment they strike. NASA plans to return humans to the moon this decade. Artemis Base Camp. Permanent habitats, mining operations, scientific outposts that could support crews for months or even years at a time. China, Russia, private companies, they all have lunar ambitions. The moon is about to get crowded, but we're sending people into a shooting gallery we don't fully understand. That December flash wasn't a freak occurrence. It was a glimpse of the lunar surface's true nature. Preliminary estimates suggest the moon gets hit by objects capable of creating visible flashes several times per month during meteor shower peaks. Between showers, the rate drops but never reaches zero. The bombardment is constant, relentless, governed only by probability and the chaos of orbital mechanics. This is why observations like the December event matter so desperately. Each flash we record adds to our statistical database. Each impact we analyze improves our models. We're essentially creating an actuarial table for lunar surface hazards, calculating the odds that a habitat module, a rover, a pressurized tunnel, or an astronaut on a surface walk will be in the wrong place at the wrong moment. The solutions aren't simple. You can't just build thicker walls and hope for the best. Mass is expensive to launch from Earth. Every kilogram of shielding is one less kilogram of equipment, supplies, or scientific instruments. Engineers are exploring alternatives, burying habitats under lunar regolith, using water ice as shielding, developing rapid response warning systems that could detect incoming impactors in time to alert surface crews. But all of these solutions require data, real data, observational data from events like what Meteor captured on December 12th. That flash of light, lasting less than a second, barely bright enough to register on sensitive detectors 250,000 miles away, represents something profound. It's a message from the cosmos, written in the universal language of physics and delivered at hypersonic speeds. The message is simple. Space is not empty. The solar system is a dynamic, chaotic environment where matter moves at velocities that turn pebbles into weapons. And we're about to send people to live permanently on a world with no atmosphere to protect them from this reality. But here's the thing about humanity. We've always been at our best when facing seemingly impossible challenges. We've learned to fly despite gravity. We've learned to live underwater despite needing air. We've learned to survive in deserts, in Arctic wastes, in environments that should by all rights be lethal to creatures evolved for African savannas. The moon will be no different. Every flash we observe, every impact we analyze, every data point we collect brings us closer to understanding the true nature of the lunar environment. Knowledge has always been our greatest tool, our most powerful technology. That December night, we added one more crucial piece to the puzzle. Somewhere on the moon right now, there's a fresh crater, perhaps a few meters wide, surrounded by a splash pattern of ejected material. Its rim still sharp and undefined by the slow erosion of micrometeorite bombardment that will eventually soften its edges over millions of years. That crater is a monument to cosmic violence, yes. But it's also a teacher if we're willing to learn its lessons. Because the next flash we see might not hit barren regolith. It might strike near or through a structure containing human beings who've traveled farther from home than almost anyone in history. And when that day comes, the data we're gathering now, the observations we're making from robotic telescopes on Earth, could mean the difference between a close call and a tragedy. The moon is waiting. The cosmos is watching. And somewhere in the darkness between worlds, the next impactor is already on its way. The only question is, will we see it coming?